My name is Morgan Hale, and I will be demonstrating a multi-stage liquid-solid washing problem. I'll be explaining a few preliminary concepts before going into the calculation portion. First, I'm going to show you how to determine the number of stages in a counter-current cascade using the graphical method. Here we have two examples of counter-current cascade systems, an absorber and a stripper. Notice that both towers are very similar, but the stages in that of an absorber are labeled in the opposite direction of the stripper. Now I'm going to create an XY graph based on a generic absorber. Here I have clearly labeled the equilibrium curve and the operating line. The equilibrium curve represents y as a function of x. This information is usually given in the problem and can be drawn fairly easily. The operating line is above the equilibrium curve in the case of the absorber, but will fall below the equilibrium curve in a stripper. This line is calculated using the pair of streams located at the top of the tower and the pair of streams located at the bottom of the tower. These points are clearly labeled as x0, y1, and xn, yn plus 1. Once these points have been identified and the line has been drawn, you can manually draw stair-like lines connecting the operating line and the equilibrium curve. To do this, first start at the x0 and y1 point. Then draw a horizontal line from that point directly to the equilibrium curve. Then draw a vertical line back to the operating line. Continue this until you have reached the end of the operating line. In this case, we have roughly 2.3 stages. This will be rounded down to 2 full stages. Pressure drop is created in a trade column by 3 factors: friction for vapor flow through dry tray perforations, holdup of equivalent clear liquid on the tray, and a loss due to surface tension. I would like to mention that liquid holdup is the volume of liquid in a pipe element per volume of the pipe element. This is the complete equation with all 3 factors, and these are the individual equations of each component. The loading point is defined as the upper gas velocity limit for a constant liquid holdup. This means that when the flow of a gas up through a liquid is too great, it will start to halt the flow of the liquid, which in turn raises the liquid holdup. Once this flow of gas is so high that it pushes the liquid further up the tower and it overflows, the flooding point has been reached. Now I have drawn the parameters for the counter-current cascade system we will be using for calculations. This is a 3-stage system with perfect mixing in each stage. I have assumed that my feed is 100 kilograms per hour, my solvent is 100 kilograms per hour, and that all of the solids remain in the underflow. Fa equals the amount of solubles in the feed, Fb equals the amount of insolubles in the feed, and Fc equals the amount of moisture in the feed. R equals 0.25. This is based off the fact that the solids product of each filter contains 0.25 kilograms of solution per kilogram of inert solid. Because all of the solids remain in the underflow, we can multiply our R rate by the amount of insolubles to achieve a value of 20 kilograms of solution per hour for all solution flow rates because they are equal due to the equilibrium state in each filter. Since we now know our solution flow rates in the underflow, we can calculate our overflow solution rates. I have assembled a series of 3 equations, one for each stage, which shows that what goes on in the filter equals what comes out. By using basic algebra, you can easily solve for V3 first, then V2 and V1. Now that we have our flow rates, we can write the solute material balance. This consists of, again, 3 equations, one for each stage. These equations require a bit more effort to solve for the unknowns. By using a program like Excel Solver, you can calculate the y values. Due to the equilibrium state, the x values are the same as these y values. In order to calculate the solubles in overflow, simply multiply the y values by the V overflow rates. This gives you a new flow rate directly related to the amount of solute at that stage. Finally, to calculate the percentage of inlet solubles that can be recovered in the product solution from each stage in the system, divide the overflow rate by Fa, our inlet feed of solubles.